cascade configurations, if you are considering a multi-transistor circuit, uh, you can have other configurations like Cascode configurations. Later on, you will also learn about differential amplifier configuration. So there could be more than one multi-stage or multi-transistor circuit configuration. For example, this figure 53 over here shows an NMOS N-channel MOSFET Cascode circuit in which the load is stacked up. It's like vertically connected MOSFETs as opposed to what we have seen earlier. So from earlier we have this cascade configuration. So starting from left to right, you have this load which is being driven by, I mean, from one stage to another stage. Okay, so it's connected horizontally, but over here the MOSFETs are like they're connected vertically. But if you look closer to this circuit, you will see that this M1 is connected in a common source configuration. So the NMOS device M1 is in common source configuration, whereas the M2 transistor has a coupling capacitor CG. Okay, just like M1 has a coupling capacitor CC, which couples the input voltage VI AC voltage. Then this for the alternating time varying signal, this is an AC ground. The gate of M2 is an AC ground, so therefore the gate is common. So M2 is a common gate configuration. M2 has a common gate configuration. So gate is the common. So what happens is, I mean, for this particular application, common source can provide you a small signal gain, whereas if you're connecting this in Cascode with a common gate configuration like this, you might end up in achieving a higher frequency response. I mean, so it has its own advantage. So the advantage of this type of circuit is a higher frequency response. Okay, so transistor M1 is connected in a common source configuration. M2 is connected in common gate configuration. So the idea is behind these multi-transistor circuits or multi-stage transistors, multi-stage MOSFET devices, is that, for example, over here, the idea was to have minimum output resistance. So we had a source follower at the output. So the M2 was source follower. Then M1 was a common source configuration which was providing us the gain. Okay, so if the gain is a requirement and the output resistance is small, then you might want to go for this multi-transistor circuit as an amplifier. Of course, M1 and M2 both has to be operated in saturation region, and therefore you have to design the circuit first such that those resistances R1, R2, RD1, RS1, what we talked before, they ensure that both devices are operating in the saturation regime. Similarly, over here, if the requirement is for the gain and at the end you need a higher frequency response, then you can have a cascode configuration like this. So it all depends on the requirements. Okay, so what the requirements are. For example, now let's consider this example as from your text 3.18. The objective is to design the biasing of a cascode circuit to meet certain specific requirements. So for the circuit shown in figure 53, okay, it's the same circuit. This is figure 53, so this is copied over here. This is 53. So the transistor parameters are, the threshold voltages are identical. The conduction parameters are identical, 0.8 milliamps volt squares. You don't need to consider the channel width modulation parameters, lambdas. So basically M1 and M2 are identical transistors, right? And both are NMOS devices. So you see, the thing is now, if you have to operate this cascode configuration as an amplifier, then both M1 and M2 have to be in saturation region. Okay, so the specifications are as such that the addition of these all three, the biasing resistance R1, R2, R3 is 300 kilos. Okay, so R1, R2, R3 is 300 kilos. Your source resistor for M1 is given as 10 Ks. So you have to design the circuit, which means find what is R2, find R1, R2, R3 independently, okay, separately, such that the quiescent current is 0.4 milliamps. Now this IDQ is the same current, same drain source current for both M2 and M1 transistors. So this IDQ is given as 0.4 milliamps. Okay, it's the same current that flows in both the transistors from drain to source, and the direction of current you can see for the NMOS device is out of the source. Okay, and you're given the VDSQs as well. So the drain to source voltages for both the transistors are the same, 2.5 volts. So one thing to consider over here is you can see that if this configuration is to be operated as an amplifier, then your IDQ, which is the same for both transistors, since the transistors are identical, we have the same IDQ. Okay, for identical transistors, we have this conduction parameter that is same again, and then you have the in the saturation region the IDQ, since it's independent of VDS, so we have VGS minus VDN, the threshold voltage, which is again the same for both the transistors. So this is whole squared. This is the current voltage relationship in saturation. For both MOSFETs, it's the same. So it's the same current, same conduction parameter, same threshold voltage, which means we are going to end up with the same gate source voltage, which implies that VGS1 will be equal to VGS2. Okay. Why? Because the transistors are in saturation and your your drain current is only depending on the gate source voltage, and this drain current in this configuration is the same for both MOSFETs. Okay, so the gate source voltage is over here. The gate source voltage for transistor M2 and the gate source voltage for transistor M1 are same. Okay, and from this fact, since IDQ is given, we can find VGS very quickly. So you see, it says since M1 and M2 are identical transistors, and since the same current exists in the two transistors, the gate to source voltage is the same for both devices. So if you use this relationship, it's independent of VDS. You find out VGS for both the MOSFET devices, and you can see that this value is greater than VDS set. Okay, for both the transistors, and VDS set determines the transition point from non-SAT to SAT region. First thing to note is that this VGS for both MOSFETs. So let's write it like this: VGS1, which is equal to VGS2. First of all, they are greater than the threshold voltage. Both of these terms are greater than threshold. That means both the MOSFET devices M1, and M2 are on. Now, if they are on, they're not in cutoff, then they're either in the saturation region or they're in the non-sat region. So VDS sat, which is given by VGS minus VTN, the overdrive voltage, is, you can easily find this out as VTN is the same for both devices, and it's given as 1.2 volts over here. So that's quite straightforward to find. This is 1.907 minus 1.2. So that's about 0.707. Okay, now you consider that this VDS, this is VDS at only. Okay, so this value is the VDS setters. This is a transition point. Okay, so VDS is 2.5 volts. Okay, so VDS is 2.5 volts for M2, and VDS Q is 2.5 volts for transistor M1. So both are greater than 0.77. That means both the transistors are in the saturation region. So your current that is flowing in the both MOSFET devices is the saturation current. Okay. So if you continue with the design, you have to find the rest of the resistances. We are given RS, okay, but you have to find R1, R2, R3. So for that, let's find out what this VS1 is. That the source voltage at the MOSFET M1 VS1 is given as, you see, VS1. If you look at this this node, well, this should be equal to IDQ multiplied by the source resistance RS, which is given to you minus 5 volts plus V negative. Okay, so that's your nodal voltage at the source of MOSFET M1. IDQ is known, RS is known, so it's the same expression over here. If you plug these values, IDQ is 0.4 milliamps, RS is 10 kilos. So then we have minus 5. Add this up, you're left with VS1 as minus 1 volts. Why do we need VS1? Is that we need VG. Okay, we need VG1 And then similarly, we will be needing VG2. Why? Because you can use the voltage divider principle to find those resistances. So from here, it's not hard to find that VGS1, which is written as the voltage difference of VG1 minus VS1 is now equal to, what is this equal to? VGS is 1.907. So this is 1.907. So to find VG1, you just add it to VS1 to 1.907. That gives you VG1 of, so if you add 1.907 minus 1, you end up having 0.907 volts at the gate of transistor M1. So this is your gate voltage for transistor M1. Now from this gate voltage, you see this voltage is basically the division of this resistance R3 over R1, R2 plus R3 into 5 volts. Okay, so what I'm talking about is you have VG1 as over here. This is your VG1. Okay, this is my VG1. So from the voltage divider principle, VG1 is given as R3 over the addition of all three resistances into 5 volts, which is equal to the gate voltage. Basically, this is the gate voltage. Okay, and this is 0.907. So you have R1, R2, R3, which is in the specifications. So the combination should be 300 kilos. So just plug it in over here. Then you have 5 volts as the supply over here, V positive, and then you find out R3, which is 54.4 kilo ohms. Okay, so you have R3. We have R3. We know what RS is. So let's go on finding R1 and R2. Now, since okay, let's do the same. Let's use the same analysis that we have used for evaluation of VS1. We find out again what VS2 is. Okay, over here we have VS2. So let's find out what this VS2 node voltage is. This VS2 is the same as VD1. Okay, so these two things are these two nodes are the same. So we know, and this is VS1. So we know what VS1 is, and we know what VDS1 is. So VDSQ1 rather is 2.5 volts. Okay, so we are given with this information. Then we can go on finding what VD1 is. VD1 is going to give you VS2. So you see over here, this is 2.5 volts. And so VD1 minus VS1, VS1 is, so if you add it up to the other side, you will get the drain voltage as 1.5 volts. So over here, VS2, or which is equal to, I can say this is VD1. This is VD1. So VD1 is equal to VDSQ1, 2.5 volts, plus VS1, which is minus 1 volt. You are left with 1.5 volts. So 1.5 volts is your the drain voltage of transistor MOSFET M1, or the source voltage, the DC source voltage at the MOSFET M2. Okay, so we have VS2. Then similarly, we know what VGS is. VGS is the same. VGS1 is VGS2. Okay, because the current is the same, transistors are identical, so we are going to use the same information to find what the gate voltage is at the MOSFET M2. To find that, once again, we have a very similar expression over here, and we find the gate voltage for M2 transistor. Okay, this is the gate voltage. So you see, in the DC analysis, we don't need to consider this capacitor. This is open, this is open, this is open. Forget about these circuit elements, the capacitances. So let's find the DC nodal voltage gate 2. So this is equal to 1.907 now plus 1.5. Okay, previously we had this as minus 1. So VS2 is 1.5, therefore this becomes 3.407. And then you find R2 plus R3 is 204.4 kilo ohms. Now since R3 is known 54.4, you use this R3 information over here to find what R2 is. R2 is 150 Ks, and since R1 plus R2 plus R3 is your 300 kilos, you know what R2 and R3 is, then you can find what R1 is. Okay, and R1 comes out to be equal to 95.6 kilo. So you have all these three resistances. Okay, all you were required to do was to find the gate voltages, VG1, VG2, use the voltage division, and then find those resistances. Okay, so you're almost done. The only resistance to be found out that remains is RD. Okay, to find that, let's find the voltage at the drain of M2, that is VG2. So the information that you have is you have VS2. VS2 was 1.5 volts. Okay, VDS is 2.5 volts again. The VDS, remember VDS1 is the same as VDS Q2. That was the requirement as such. So these two voltages are equal. Okay, over here this is equal. So so 2.5 volts plus VS2 gives you 4 volts. VD2 is 4 volts. Now if you take the potential difference between this point, the potential difference of these 2 points, this point is basically VD2, the output voltage. Okay, DC output voltage. Then 5 minus VD2 over IDQ is going to give you RD, which is 2.5K. So we have done determining all the resistances that ensure that those two transistors are in saturation region, which is indeed the case. I mean, since VGS is the same, so VGS minus VTN, as we have said before, that determine the saturation point is the same for two MOSFETs. So that for two MOSFET 1 and 2 is the same. So that is again VGS minus VTN, and VGS is 1.907 for both the MOSFETs, minus VTN 1.2, that gives you 0.707. Then for both MOSFETs, you have the VDS as 2.5 volts. That means both transistors are in saturation region. So this IDQ is the saturation current, okay, as we previously talked about. So that's how you design the Cascode configuration for the given specifications. Okay, again, these specifications are according to the requirements, according to the application which you're going to put your circuit in. So the requirements could be a high frequency response with a certain gain. So you might go for a Cascode configuration. The requirement, like this we have talked before, was if the requirement was as such that you need a minimum or a very small output resistance R naught, then you might want to go for a cascade configuration with a common source cascaded with a source follower configuration. So you have a small output resistance with a certain gain over here that is being provided by common source already. So multi-stage or multi-transistor configurations all depend on the requirements. Okay, possibly one of the stage is not enough to give the gain, so you might need to cascade the other stages as well. So it all depends on the requirements how you are going to design the circuit. But again, the designing has to start with the DC analysis. So you know what is the operating regime of the circuit is. If it has to be operated as an amplifier, then the transistors have to be in saturation or the active region. If you have to operate them as a digital switch or in digital logic functions, well, then it can be operated in non-sat and sat regions. Okay, or you might want to use the cutoff region as well. If the transistor is to be used as a switch, then it can be in non-sat. It could be in the cutoff or it could be in the sat region. Okay, for digital logic functions, it could be non-sat and sat. Okay, so it all depends on the applications. So you see, for both MOSFETs over here, for amplification purposes, each transistor is biased in the saturation region, which we have already found out. This was 0.71 volts. So our VDS was 2.5 volts, which passed beyond 0.71 volts, meaning each transistor is biased in the saturation region.